Biochemistry. I'm going to go over the homework problems that you had yesterday, and then we're going to talk about naming covalent bonds. Now, I know covalent bonds are in your next chapter, but we're going to go ahead and get this naming out of the way since it all kind of works together. So, one thing I do want to mention is that acids, this right here is actually a covalent bond involved in acids, but we put it in terms of naming over on the left side of that chart, and I think you'll see why when I talk to you about how to name covalent bonds, because they kind of follow the ionic bond ruling, sort of. I don't know, they're just a little bit different. Anyway, H3P, this is a binary acid, so we use hydro, phosphoric acid. Okay, this is a polyatomic anion, and this is the phosphite. So that means it is phosphorus acid. Okay, this is another polyatomic anion. It is the phosphate anion. So it is phosphoric acid. Alright, now we're going the other way. So if we look at this name, sulfuric acid, we know that it is not binary because there's no hydro in front. We know that it has the 8 form of the ion because it has ic there. So I'm dealing with the sulfate polyatomic anion. Has a -2 charge. My cation is hydrogen, which has a +1 charge. So when we balance the charges, our least common multiple here is going to be 2 plus 2 -2 equals 0. That means I have to have 2 times +1 to give me +2, and then one of these. So the formula is H2SO4. Alright, this is sulfurous acid. There's no hydro, so I know it's polyatomic, and it is the ite version. So the sulfite version, this is SO3 with a -2 charge. We have to have hydrogen cation with a +1 charge. When we balance out these charges, just like we did above, the formula is H2SO3. Okay, hydrosulfuric acid. Since we have hydro here in front, we know it's binary. That means there's only 2 things involved. That is my hydrogen cation, my sulfide IDE anion. I know that's a -2 because I look on the periodic table and it is in the oxygen family. So in its monatomic anion form, there's a -2 charge. So when I balance these out, the formula is H2S. Alright, I'm going to go back to my chart. Now we're going to learn about naming covalent bonds. Now, covalent bonds are between nonmetals, and we're not talking about polyatomic ions here. No matter what, you have to determine the cation charge. when you're using IUPAC nomenclature. Now, there are two ways to name these. There's the IUPAC way, and there's the traditional way. So for the IUPAC way, we do it the same way we did when we were naming multivalent metals. And that is your cation, the Roman numeral, and I'm just using the Roman number for Roman numeral. And remember, this is your charge, not how many. Okay, that's your charge or your oxidation number, not how many. And then you write the anion name. So an example would be CO2. We have to determine the charge of the cation from the anion. So we have to work backwards here. Oxide ion is always going to have a -2 charge. I have 2 of them, so my overall negative charge is -4. So this has to be a +4. I have 1 of them, so 1 times the oxidation number of +4 would give me an overall positive charge of 4. So the oxidation number of this carbon here is +4. So we would say carbon, Roman numeral 4, oxide. Now you're probably familiar with the traditional name. Let me tell you how the traditional names work. Traditional names use the Greek prefixes mono, di, tri, tetra, penta, or sometimes just pent, hex, or hexa, which, by the way, hex is German for witch. Like if you put a hex on somebody, and it's 6, the number 6. So like the number 6 is like an evil number, and in German, a witch is given that name hex, or at least part of that name. I might be a little bit wrong on that, but hex is involved in that name. Hept, H-E-P-T, is 7. Oct, 8, like an octopus, or the octet rule. Nona, N-O-N-A, is 9. And deca, like decade, or decameter, is 10. Okay, so the way that we name traditional covalent names is we put a prefix except for mono. Mono would not go in front, and I'll tell you what that means in a minute. Okay. This prefix tells you the number of atoms. I didn't realize you couldn't see that. I apologize. Okay. And then the name of your cation, and then a prefix which represents the number of your anion atoms, and then the name with IDE at the end. Okay, so you all probably recognize CO2 as carbon dioxide. Now, notice I said up here you would not use mono in front of a cation. So think about it, you never hear monocarbon dioxide. Okay? If there's only one cation, then you just leave the mono off and you say carbon dioxide. I'm going to do some more examples for you, and then I'm going to give you some work to do. Okay, so let's look at this example. CO. We're going to determine our cation charge here. We've got one carbon, we've got one oxygen. The oxide monatomic anion is always going to have a -2 charge. So 1 times -2 is an overall -2. In order for this to equal 0, this has to be a +2. So 1 times a +2 would give me a +2 overall charge. So the IUPAC name is carbon 2 oxide. But the Roman numeral name, the traditional name, blah, 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 is carbon monoxide. Notice that we do put the mon instead of mono here, but we do not put the mon or mono in front. Let me do an example where you have to use a prefix in the front. N2O5. Again, we're going to determine that charge. Oxide would have a -2 charge, so 5 times -2 would give you an overall -10 charge. So your cation charge would have to be an overall +10. 2 times what will give you a +10? Plus 5. 2 times plus 5. So this is nitrogen 5 oxide. And then the traditional name is going to be dinitrogen pentoxide. Okay, I'm going to give you some problems to do. Notice that this is not the polyatomic anion. Okay, so this is not sulfite because there's no charge. Okay, so for these, you're going to give me two names. This, you're going to give me a formula and the other name. And this, you're going to give me two names. Y'all have a good day.